Hello guys, I am Pratham Prasad from India. Today we will be proving an exciting result. Summation m equals to 0 to k, kcm whole square is 2k ck. It is our lemma 1. The proof goes as with generating functions. First define the inner function f of m equals to summation I nci mcr minus I wherever it is defined. Now putting this inside of our capital F of x to define the actual generating function. So we get summation on m, summation on I, and whatever is inside, and attach this x to power m outside. Now sending the second summation inside, we get summation on I nci, as it is independent of m, it is outside the summation of m, and using the lemma 2 here, we get the following: summation I nci x to power r minus I 1 minus x to power r minus I plus 1. I will be proving lemma 2 later. So now taking out the term independence of I outside, we get this, and using binomial theorem here, we get this. Now we will again use lemma 2 here to get the expansion of f of x. Now taking the coefficient out, we get the proof of summation I nci mcr minus I equals to m plus ncr, a more general version of our lemma 1. Now putting m equals to r equals to n, we get the desired proof of our lemma 1. Now getting started with lemma 2. Summation of kcm x to power k equals to x to power m by 1 minus x to power m plus 1. There are tons of proof on the internet, but my favorite and what I made actually is from differentiation. We will differentiating 1 by 1 minus x m times with respect to x to get m factorial by 1 minus x to power m plus 1. You can see the results, the patterns of the first derivative is 1 by 1 minus x whole square, the second derivative 2 by 1 minus x whole cube, and with induction you can prove it. So I am skipping all that part as it is very basic, and the second is also a known result. Now rearranging a bit, we get the desired proof. You can see very well. Now let me define In be integral 0 to pi by 2 sine of n theta cos to power n minus 1 theta d theta, and similarly we get In plus 1 by putting n goes to n plus 1 and taking the difference and applying integration by parts, we get this recurrence relation. Now for evaluating it, let n tending to k, so 2k plus 1 by k, I of k plus 1 equals to I of k plus 1 by k. So taking ik on the other side and multiplying both sides by 2k plus 1 factorial by k minus 1 factorial, we get the following. Now taking the sum from k equals to 1 to n minus 1, we get n by 2ncn in minus 1 as I of 1 equals 1. So our telescoping sum now gives us the value of in very nicely to be 2 to power n by n times 2n choose n times summation of k equals to 0 to n minus 1 1 by 2k 2k ck, the central binomial coefficient in other words. Also observe that I used a very nice property of double factorials and factorial relating to binomial coefficients. You can easily prove it by expanding the double factorial and multiplying with k factorial. Now using our in value, we get integral 0 to pi by 2 sin n theta cos of n minus 1 theta equals 2 to the power n by n times 2n choose n times summation k equals to 0 to n minus 1 1 by 2k 2k ck. Multiplying both sides by 1 by n, we get the following. And observe, we are getting closer to our sum as I have shown in the thumbnail. So now manipulating and using lemma 1 here, we get the following. Now you can see that this side we are having an integral and the other side is just very close instead of one more summation. Applying that summation n equals to 1 to infinity, we get the following. And using now sin n theta is an imaginary part of e to power I n theta, we get the following manipulations. Now taking the imaginary part of log of 1 minus cos theta into e to power I theta, that is obtained by the power series of log n, log 1 minus x I guess. So now taking the imaginary part You get arc tan sin theta cos theta by sin square theta, and the negatives cancel out with the negative of the negative imaginary part. So we get arc tan of cot theta equals to pi by 2 minus theta, and applying King's rule of integration, we get a beautiful representation of our summation in terms of an integral x equals to 0 to pi by 2 x by sin x dx. All that remains to evaluate is just an integral. So putting x equals to 2u, we get 2 times integral 0 to pi by 4 u by tan u times secant square u du. Applying integration by parts again, we get minus 2 integral 0 to pi by 4 log tan u du. You can see the steps very briefly. I am not explaining much of it because it is very basic. And you know the integrals in our channel are not so basic. So we have to skip some steps to keep the video ideal. Now, substituting tan u equals to y, we can see the manipulation of the differential coefficient alongside. S equals to minus 2 times 0 to 1 log y by 1 plus y square dy. Now employing the power series of 1 by 1 plus y square, or rather 1 by 1 minus x, and substituting x equals to minus y square, we get the following. Now we are getting an integral of integral 0 to 1 y by 2n log y. I have used clever manipulations, as you can see, using one limit and differentiating another integral sign to get the log x term. So evaluating inside out, we get the following, and at last we are left with the definition of the Catalan's constant. So s equals to 2 times g. G represents Catalan constant. So now relating to our sum, s equals 2g or 2 times the Catalan constant. Thank you for watching.